Hello, this is David Ferris, and this video is covering Week 3 in STAT535. This is Part B of the lesson. You should have already watched the first part, which is over normal calculations. And now we're going to take that skill set of calculating percents in normal models and apply it to a whole different ballgame. In fact, I can't really emphasize enough how important this next section is to your understanding of all the other sections that we're going to cover, because we're taking a whole different turn with data and sampling and distributions. And what we're covering today is something called sampling distributions, with the emphasis on the ing. These are distributions that are created when you do lots and lots and lots and lots of sampling. When you do lots and lots of sampling, you're creating a completely new kind of distribution. So let's start out with something very simple. Here's a data set that only has 4 numbers in it. And of course, they could be in any order. They could be 1, 2, 3, 4, but apparently the way they were collected is a little out of order. There's a context here that these were the number of mistakes made by some people on a project. So if you take these 4 numbers, which makes a data set, if we would just find the mean and the standard deviation of these 4 numbers, the mean wouldn't be too hard. If you add these numbers up, that's 10. 10 divided by 4 would be 2.5 mistakes. So on average, this group of people made 2.5 mistakes per person. And then the standard deviation, of course, would have to be calculated likely with some technology. So if you type these 4 numbers in an Excel list and did STDEV to these 4 numbers, you would find out that the standard deviation is 1.12 mistakes. Just to review, standard deviation is essentially the typical, you could even call it the average variation from the mean. So if you look at the mean being 2.5, these numbers vary on average from 2.5 by about 1.2. Now here's where we take a twist that makes this a little more complicated, a little more difficult. What we want to do now is find all the possible means of samples when we take 2 employees without replacement and average them together. So in other words, if you took 2 of these numbers and added them up and divided by 2 to get the average, we want to find all possible means, all possible averages when you pick 2 and average them. Now, because there's 4 numbers, there will be 16 different means altogether. So I would probably, if I were doing this by hand, do it sequentially so I don't forget any. So like, for instance, we could pick 3 and 3. We could pick 3 and 2. We could pick 3 and 1. We could pick 3 and 4. And each time we would be averaging them. So for instance, if we put 3 and 3, averaged them, you get 3. If you pick 3 and 2 and averaged them, you get 2.5. If you pick 3 and 1 and average them, you get 2. If you pick 3 and 4 and average them, you get 3.5. And you would do that for all 16 of them. What we now have here is something completely different, because every single one of these numbers is a sample mean. It's a mean from a sample. The notation we use for sample means is X bar. So essentially what we're going to have here in this data set, actually that's not really the right word. It's not a data set. It's a set of means. So we will have 16 means, 16 sample means. And it would be all the possible ones that are that one could calculate from 4 numbers like this. And so it would be much easier, of course, to do this with technology. So let me switch gears and go to Excel. And what I have done is put the 4 numbers in the data set. I've actually put them in order, just because it would be easier to think about. So there's our data, 1, 2, 3, 4, and I added all possible pairs of them, and I got these numbers, and then I took the average of these, divided each of them by 2 basically, and got the 16 averages. So in this list of blue numbers, these are the 16 means from the 16 possible samples of 2 numbers. And if you'll notice, the histogram for all of these is perfectly symmetric. perfectly symmetric. So we've got 1, 1, we've got 1, 4, we've got 2 1.5s, we got 2 3.5s, you got 3 2s, you got 3 3s, and the most common number we have is 2.5. There are 4 2.5s in this list. So notice how perfectly symmetric it is. And not only is it perfectly symmetric, but one might even possibly, might be a little stretch, but might even say that it's approximately normal. So now you can see the tie to what we just learned in the first half of the lesson. These distributions, many of them are going to be approximately normal, so therefore we'll be able to calculate a lot of normal calculations with these special distributions. Now you'll notice something while we're here, that the mean of these 4 numbers originally, 1, 2, 3, 4, the mean was 2.5. And the standard deviation was 1.12. We wrote that down earlier. Notice when you graph all the possible means of sample size 2, the mean of the means is the same, 2.5. You can see it clearly here. You can see it even with the numbers. So the mean of the population is going to turn out to equal the mean of all the possible sample means. However, if you look at the standard deviation, you'll notice the standard deviation is much smaller. When you start taking averages and plotting them, they will not vary as much as the original data did. And you'll see that in a lot of cases when we do this over and over. All right, so if we go back to our handout, our graph, I said sketch a graph, it was basically very symmetric. And let's see, how many did we have here? 1, 2, 3. So the fourth one was the tall one. And this is very crude sketch, but there it is, roughly. And if we were doing this really accurate, we'd put the labels on there, and we'd have an axis that had the counts and that sort of thing. But the general idea is just to see that, oh yeah, this distribution is approximately normal. So this distribution, because it's very special, has a special name, and it's what the title says there. This is called a sampling distribution. ING is very important. A sampling distribution is very different. Every single thing that you're graphing here is a statistic. So a sampling distribution is a distribution of statistics, not data. Every single one of these numbers that we were graphing, and this is kind of what the graph looked like, every single one of these was not a piece of data. That 3 came from the average of 3 and 3. The 2.5 came from the average of 3 and 2. The 2 came from the average of 2 and 2. The 3.5 came from the average of 3 and 4. Every single one of these things we graphed was a sample mean in and of itself. So we have to think a little differently when we're thinking about these. They have different parameters, and we will have formulas that we need to be very careful when we're calculating. So we found out already on the Excel document that the mean and the standard deviation of the sampling distribution, the mean and the standard deviation of the sampling distribution, we found out 2 things. First of all, the mean of all the means was the same as the mean of the population. So 2.5 mistakes was also the mean of the sampling distribution. But the mean, or the standard deviation of the sampling distribution, was not the same. It was a little bit smaller. It looks like it was 0.79 was the standard deviation. So the standard deviation was quite a bit smaller, or at least it was noticeably smaller. Also, notice the notation we're using. We're saying the mean of all the, and look at that little subscript there. It's the mean of the means. That's literally what that means. The mean of the means, or the mean of the pile of the means, is 2.5. That's what we're finding when we're finding mu sub x bar. And then the notation here is also very specific. We're finding the standard deviation of all the x bars. The standard deviation of this pile of x bars was 0.79. So we will use technology to find the standard deviation usually. And the mean is always just going to be the mean of whatever population you started with. So we will be able to use even the formula on a list in Excel is just going to be the standard deviation of the population, because we have all possible sample means in here, so we're using the standard deviation of the population formula to calculate that. Now, because though we do have a different standard deviation, it's not just the standard deviation anymore, it's the standard deviation of a bunch of sample means. We need to call it something different so that we don't confuse it from, say, the standard deviation of the population. So many textbooks decide to call that the standard error of the mean. So we are now going to call this right here the standard error of the mean. And we use that terminology when we have a standard deviation of a sampling distribution, or the standard deviation of a bunch of x bars in this case. And the word error is kind of interesting. It's a word that really just means deviations or variations. It does not mean mistake. This is not like the standard mistake of the mean. That's not what it should indicate. The word error in statistics generally just means variations or deviations. Now, it does turn out that there's two ways we could have calculated that the standard deviation of this sampling distribution was 0.79. I did it by just having Excel calculate. In fact, I guess I can show you here. Here's the formula up here. I had Excel do the standard deviation of the population of these blue numbers. That's one way to calculate it. However, there is a formula. So using the formula, there's a formula that says, another way to find it is to take the standard deviation of the population, 1.118, and divide by the square root of the sample size. So let's just see if that really does work here. Let's type a formula that says, all right, I want to take this number, 1.118034, and divide by the square root, SQRT, of 2. And when you hit enter, you'll notice it really is. So there is a shortcut for finding the standard deviation of the sampling distribution, which we're now going to call the standard error. In fact, I should probably just make that correction right here. This is going to be called standard error of the means. The standard error of the means can be found by taking the standard deviation of the population and dividing by the square root of the sample size. So that's what this next formula is showing us, that a shortcut is to take the, in other words, to find the standard error of the mean. We can take the standard deviation of the population, which is denoted with sigma, but sigma was 1.12 up here, and divide by the square root of the sample size. The sample size was 2. So in this case, we would divide by the square root of 2. And we could have gotten that in kind of a shortcut fashion. So we now know how to find the mean and the standard deviation of a sampling distribution. The mean is always the same as the mean of the population, and the standard deviation is always sigma divided by the square root of n. Now I'd like to go to this website. You can go there now or later, but I will go there now and demonstrate exactly what is going on in more of a kind of an animated sort of way. So imagine this is the population of penny ages. I've actually done this with my students, and this is generally what it looks like. So most pennies that you sample from just going to stores and things are going to be within 10 years old. But every once in a while, you'll get some pennies that are 20 years old or 30 years old or 40 years old or even 50 years old. And so if you took a population of the pennies that are out in circulation around any given city, it's probably going to look something like this. Very, very skewed to the right. It's a great distribution to demonstrate sampling distributions. And so now what we're going to do is we're going to take a sample of 5. So you'll see 5 pennies drop out of this population. And then right after the 5 pennies drop out, it's going to calculate the mean, x bar, of those 5 pennies, and it's going to drop the mean down on this third line. So let's see how that works. Here comes 1, 2, 3, 4, 5 pennies, average the age, drop it down. So we have three different distributions here that are being created by this animation. Let's do it again. 1, 2, 3, 4, 5 penny ages, and then the mean drops down. And one thing you'll notice, even though the penny ages are wide in variety, by the time you average these 5 pennies, the average really is pretty centrally located. So keep that thought. 2, 3, 4, 5 pennies. There's the mean. 1, 2, 3, 4, 5 pennies. There's the sample mean. 1, 2, 3, 4, 5 pennies. There's the sample mean. 1, 2, 3, 4, 5 pennies. There's the sample mean. 2, 3, 4, 5 pennies. Sample mean. And so basically, if you did this a long time, you sampled 5 pennies from the population and graphed the average age, you can kind of see what's forming. I think you can kind of anticipate even what might be forming. Because even though you might get this weird old penny over here, by the time you average it with the other pennies, the mean is really not that far from the rest of them. So you might anticipate what's going to be forming here if I did this a long time and I graphed all these means. In fact, you can imagine every single one of these little blue boxes is really an X bar. A sample mean, sample mean, sample mean, sample mean, sample mean, sample mean. So let's stop the animation and let's do 5 at a time, 5 at a time, 5 at a time, 5 at a time, 5 at a time. Are you anticipating yet what's forming? Let's do 10,000 at a time, 100,000 at a time. I think that's probably enough. You can start to see yet again. In fact, I've got a little button here I can click that says fit normal. Look how close that is to a normal distribution. Now actually you can still see a little bit of the skewness. The original population was heavily skewed to the right, and you can see still a little bit of that skewness left over in the sampling distribution. So we haven't lost all the skewness of the population, but it's, it's fairly normal, approximately normal. Might be good enough to use a normal model with. So let's check our theory here. Remember, we just got through saying that the mean of a sampling distribution is supposed to equal the mean of the population. Well, look at that. After doing 110,000 sample means and graphing them down here, sure enough, the mean of the sampling distribution is exactly the same as the mean of the population. So that seems to be true. What about the standard deviation? The standard deviation of the sampling distribution, which we call the standard error, 3.11, is supposed to be 6.94 divided by the square root of n. So let's see if that works. If you have a calculator, you could take 6.94 and divide by the square root of the sample size. Sample size, remember, was 5, so this time we divide by the square root of 5. And I'm pretty sure that if you calculated that, it's going to be awfully close to 3.11. So the standard error, or standard deviation, of this sampling distribution is in fact following this formula. So 3.11 does seem to be pretty close to the formula in theory that it's sigma divided by the square root of n. That's the formula we're going to be going by. So this simulation should show or verify that the formulas were all correct. But you did notice that there was just a little bit of skewness. If you look at this, there's a little bit of skewness left over from the population. So here's something else I can show pretty quickly, I believe. So let me clear that. What if we bump up the sample size to something bigger, like maybe 16? Did the same sort of thing. If you drop them down, we're going to drop 16 pennies this time. If you have more pennies dropping down and you calculate the mean, and you do this over and over and over, maybe you can guess what's going to be different about this. You have more data, more evidence. If you have more data, more evidence, you should be more accurate, which means, I don't know if you can tell, but the width of this distribution is not quite as wide. So we have a approximately normal distribution again, but it's not quite as wide. It's only 1.75. Well, of course it's not going to be as wide because remember the formula to go from 6.94 to 1.75, you're dividing by the square root of n. Well, we just made n bigger. When you make n bigger, that makes the denominator bigger. That should make this number smaller, 1.75. The other thing that's maybe a little harder to tell is that when we increase sample size, the distribution is now more normal. You don't quite see that leftover skewness as much. There might be just a teeny tiny bit, but it's really hard to see now. So a bigger sample size also gets rid of the skewness. So if you bump it up to 25 and do a bunch of them, it's even smaller yet, and it's getting more normal. That's a little hard to see with this simulation, but that's also a truth. When you have a larger sample size, the sampling distribution not only gets less variable, but it gets more normal. So we'll come back to that a little bit later. So let's go back to our handout. This is just a little reminder of that activity. This would be a good time to look at book problem 7.1 in your textbook. Just really to show that when you see that you're dealing with a sample and they're talking about finding what's the probability that something is less than 95 or between 95 and 97 or above 102, we're doing those same problems with a normal model, and we're trying to find, okay, what's the probability that something is less than 95, that sort of thing. So we're building a normal model, but what we have to remember is we know how to find the mean. The mean's going to be the same as the population, but the standard deviation of this sampling distribution is going to be sigma divided by the square root of n. So for problem 7.1, the standard deviation that we want to use for this problem is going to be 100, which is, 10. Sigma was 10 in this problem, and we have to divide by the square root of our sample size, which is 25. So the standard deviation is going to be 10 divided by 5, which is 2. So when we're doing this problem, the mean is 100. So, yeah, I kind of mislabeled that. So I should have not drawn my picture just yet. So let me see if I can get rid of this real quick. I don't know if I can do that or not. I may have to just draw another one. So let me just draw another quick picture here. This is where you point out that it's really important to read the directions carefully first time. So the mean of this problem was 100, and we were trying to find the probability that it would be less than 95. So 95 would be here, less than 95 would be this area. So we know the mean is the same as the population, but now we figured out that the standard deviation that we want to use for this pile of x bars is going to be 2. So we now are going to do it the same way we did those other problems in the first section of this lesson, and use your normal calculator either on PHStat or online to figure out the percentage that's below 95. Just make sure you use 100 for the mean and use 2 for the standard deviation, and that should do it. So always watch out for problems that are talking about samples. If it's samples, you're likely going to have a different standard deviation by dividing by the square root of n. All right, so now let's see. Oh, here's how I can, I guess I had to delete these piecemeal. So let's move on. There is a theorem that's good to read in your textbook. It's a pretty major, it's a central theorem. That's why it's called the central limit theorem. I'll let you read that. And all of this right here just summarizes what we all talked about, just puts it all in one place. So we now know what the shape is of a sampling distribution. We know how to find the mean of a sampling distribution, and we know how to find the standard deviation of a sampling distribution. Everything we need to know to do calculations. We also found out what happens when you increase the sample size. When you increase the sample size, we have less variability, and we have a distribution that's more normal. Sorry for the bad handwriting. We have less variability, and it's a distribution that's more normal. What happens if n is small? Is it still going to be approximately normal? Well, I believe you saw in the demo that when n was, say, 5, that was pretty small. When n was 5, we really didn't have maybe a perfectly normal distribution. We had still some skewness left over. If you fit a normal model on there, you probably remember that it didn't hit quite as well as we would like, perhaps. It's a little bit off of being perfectly symmetric. So the reason that is, of course, is the original population was heavily skewed. So when you have a heavily skewed parent like this, then there's no guarantees on getting rid of all the normality when you have a very small sample size. So I'll tell you what, let's do this. What if the original distribution was normal? So what if the parent distribution was relatively mound-shaped and pretty symmetric? What if this was the parent distribution? What if this was the parent distribution? What we'll find out is even with a small sample size, if the parent distribution is relatively normal, then you're going to find out that the sampling distribution is also fairly normal, even with a small sample size. So let me see if I can change this to a normal. There we go. There's a really nice population that's fairly normal, and if I did a sampling distribution, even with a small sample size, it's much more normally distributed. So the answer to that question is, when you have a small sample size, like say n equals 5 or n equals 2, you're still going to have a relatively normal sampling distribution as long as the population itself was normal. But if you have a heavily skewed distribution, then that's not true. If you have a heavily skewed distribution one way or the other, then when you do a small sample size, you will still see some of the skewness left over in the sampling distribution. Another thing that would be good to point out here is the difference between the three kinds of distributions you can see here. So if we did an animated here, there's 1, 2, 3, 4, 5, like we did before. This first distribution is the population. So this is the population distribution. The second one is the sample distribution. This is just 5 numbers that dropped out of the population. So this is a sample. This is the distribution of the sample. And then this blue one down here, this is the one we're talking about in this lesson. This is the sampling distribution. That's the one that's a little bit different and a little trickier to work with. So population distribution, sample distribution, sampling distribution. This comes from doing lots and lots of sampling. This would be a good time to stop the video and actually do these homework practice problems. 6, 7, 8, and 10, not 9, but 6, 7, 8, and 10. Those are all practice problems over that same material that we just covered. And then come back and we have just a really short piece to end with. So the final thing, if we were to take a sample of people and ask them, were you born in Indiana? Maybe they said yes, 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 no, yes, no, no, yes, yes, yes. So let's say we had 10 people and we asked them if they were born in Indiana and we got 7 that said yes out of 10 people. That would be 0.7 or 70%. This is going to be called P in your textbook. P, just plain old P, stands for the sample proportion. Some sort of a calculation, like 7 out of 10 people were born in Indiana. 70% were born in Indiana. The letter pi, strangely enough, is used for the population proportion. So if this was our class, the population would be all the students that are meeting currently tonight in the building, whereas our class is just a sample. So our class's proportion born in Indiana would be P. The true population proportion of all Indiana Wesleyan students here today would be pi. Many times pi is not something that's easily to obtain and perhaps totally elusive, but we can usually get some sort of a sample. So that's one thing you'll have to calculate on the quizzes, is just take some data like this and calculate the sample proportion. It's just a simple fraction and a division. So now let's say we picked a person in the room to be the Reese's Pieces CEO, and they declared tonight that from now on there will be 47% orange Reese's Pieces. What would happen if we sampled from the population of all Reese's Pieces, and we made the population proportion 47%, and we did sampling just like we did in that other simulation? So this little applet is going to sample taking 25 Reese's Pieces out of the population of all Reese's Pieces, and then calculate the proportion of those that are orange. So this one was 52% orange. The next one, if they draw 25 Reese's Pieces out of a bag, out of the population, this time they got 28%. So you notice there's a lot of variety. Let's turn off the animation and let's bump up the samples. Let's do 10 more, and 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 maybe 100 more. We can do this very quickly, 100 more. What's being graphed down here is very similar to what we just saw with the sample means, except now we're graphing sample proportions. Well, no surprise again, the sample proportions are turning out to be approximately normal, just like the sample means did. So once again, what we're finding is that when you take samples, lots and lots of samples, the sampling distribution under certain conditions tends to be approximately normal. And if they're approximately normal, then we can do all those normal calculations to it. So just like with sample means, we are also going to have some rules for sampling with proportions. So here's the bottom line, just very similar. So I'm kind of going fast because we've kind of done this already once with the other type of statistic. So when you are sampling sample proportions and you graph sample proportions over and over and over, the distribution that emerges out of that, which we just looked at with the sample with the Reese's Pieces, the mean of this distribution. In fact, I guess I could just do it with this one since it was a summary. So here's what's going to happen over a long period of time. If you do lots and lots of samples and calculate the percent orange, the mean is going to be the same as the mean of the population. So if we go back and figure out, see what the mean of the population was, or I used the wrong word, actually the percent population. Way back, the percent orange was declared to be 46% from the simulation. So we know that 0.46 is the mean of the sampling distribution as well. Every single dot here is a sample proportion. We also can calculate the standard deviation of all of these sample proportions. It's a little bit more complicated formula. You have to take pi, which pi was the true percent orange in the population. That was 0.46 in this example. 0.46 times 1 minus 0.46 over the sample size. The sample size in this simulation was 25. So what I'm doing is I'm using this formula to calculate the standard deviation of this distribution of p's, sample proportions. And when you do that, you get the number that you would use for the standard deviation of this sampling distribution. And then there's just one other little thing. We know the mean is the same as the population. So 46% was the true percent orange, so we know that's the mean of this sampling distribution. We just calculated the standard deviation of this. And then the shape is going to be normal as long as the n times p and the n times 1 minus p is greater than 5. As long as that checks out, we can assume that this is normal enough to do our normal calculations. So there's a book problem that would be good if you want a little practice before you start typing answers in to PhStat or to my stat lab. So you could practice that and look at the answer. Or if you just want to jump in and do your homework practice problem, this one problem, number 9, is a problem like this where you'll have to calculate the standard deviation and the mean and do some normal calculation. So that's a quick time through the second half. I, again, cannot emphasize enough how important these calculations and the understanding of sampling and the sampling distributions is to future topics in this course. So be sure that you have a really good understanding of this before we move forward. As always, if you have any questions anytime, please let me know. I'll see you in class.